Okay, so some classical examples in partial differential equations. So last year we treated a few partial differential equations. So and mostly we used to treat them with a well-founded substitution, and none of the time, as I remember, did we introduce some initial conditions or boundary conditions. So this is going to be a lot more precise, and let's see what we have. Okay, we are going to consider a very specific type of second order linear differential equation, by the way, which englobes a lot of very interesting things. All right, so what is the kind of thing we're going to look at? First, we're going to work with two variables functions, and we're going to work with differential equations, partial differential equations, up to order 2. Okay, meaning that we're going to have some order 2 partial derivatives, so d2f over dx square, d2f over dx dy, the cross derivatives, and d2f over dy square. Okay, and then you will have some order 1 term, so involving the df over dx and df over dy, and possibly f and equals to, well, 0 or maybe something. Well, it's going to depend. All right, so that's the kind of thing we're going to look at, and it's going to be again linear, because non-linear ones, we don't really have any method for solving them. They are really some of the mysteries of the universe, and it really depends on the kind of equations we have. Whereas here we're going to be able to classify them. Okay, we're going to be able to classify them. That's going to be the first part of this lesson. We're going to have a very, well, 3 names called hyperbolic, parabolic, and elliptic equation. And we're going to see some of these examples. All right, so let me erase that. Some nice examples, right? So we're going to study the heat equation, right? So maybe you remember from the videos of 3 blue, 1 brown about the Fourier series. He was talking about how Fourier was solving the heat equation when he discovered that, well, he established the Fourier series. This is going, so we will have Fourier series again, all right? So you must know how to deal with it. You must be okay with Fourier series now, all right? So that's going to be one of them. We're going to have the wave equation that can, well, in unbounded domain, so it can describe many things. For instance, throw a stone in a lake, you will observe some waves, and that can be something that can be described by the wave equation, but that's really one example. You've got thousands of them. We're going to work on the wave equation in bounded domain, the one that can, for example, can describe the vibrating string, so the string of a guitar or of a violin or whatever. Okay, so that's going to be our next example. And finally, we will have the Laplace equation. So again, that's another kind of heat equation, but when we have constant time and it's in 2 dimensions. Okay, so well, it's also something you can find in many things. So if you've had a glimpse of the lecture notes, you will see that we're talking about Fourier many times. All right, so meaning the Fourier series, that's going to be something important here. Okay, and we will have a lab next week about solving those equations. So let's begin, and let's have a look at the different classifications we can have. Okay, so this is it. We said we want to look at second order differential equations, meaning you will have terms d2f dx2, d2f the cross derivatives, and the second derivative according to y squared. Okay, so as it's linear, we're going to have a sum of those 3 kinds of derivatives, right? And according to the different respective values of the coefficients a1, a2, and a3, we are going to be able to classify those equations as three different kinds of cases. So let's see how that works. So if you remember the problems we treated last year, it relied mostly on the fact that we could find some well-chosen substitution. Here, let's see that with some well-chosen linear substitution, we will be able to simplify a bit that second-order term, all right? So the well-chosen substitution is that one, all right? So let's go. We need to find the partial derivatives of order 2. All right, so let's see, we have defined that capital X, f tilde of capital X, capital Y was equal to f of xy, and here I've got that capital X depends on capital X and capital Y both depend on the small x and y, so we've got this one. Lambda 1x plus y, lambda 2x plus y. Okay, so it's a very linear, very typical linear substitution, right? X and y are just going to be linearly related, right? And so I want to compute d2, well, df over dx. Okay, so if you remember, that's the kind of things we did last year at the beginning of the year. So that's just going to be the derivative, the straight derivative according to x of my f tilde function, L1x plus y, L2x plus y. So that's just going to be, so remember, so x dx over dx, df tilde over dx plus dy over dx, df tilde over dy. Okay, if you remember that. So we're going to have lambda 1 df tilde over dx plus lambda 2 df tilde over dy. Okay, so that's equal to d over dx of f. So now I need to do the second order derivative of this one. So that's just going to be the d over dx of df over dx. So that would be, let's go again. So lambda 1 times dx over dx d over dx of, I've got d f tilde over dx. So I'm applying the same method. So that was about the first term, then plus lambda 2 dy over dx d over sorry, that's still on working on the first term. D over dy of df tilde over dx plus, so let me just underline this. That term, if I apply that derivative again, that is going to give me those first two terms here, and then I'm going to treat the second one, so I get plus lambda 2 times dx over dy, sorry, dx over dx, I'm still doing the derivative according to x, of d over dx of df tilde over dy plus lambda 2 dy over dx d over dy of, so that was it, df tilde over dy. Okay, so that corresponds to, let me choose a nice color, to that one, all right? To the d over dx of lambda 2, which is just my constant, df tilde over dy, all right? So still expanding that, we obtain finally that d2f over dx2. That will be given, so lambda 1 square, d2f tilde over dx2 plus lambda plus lambda 2 square. No, that's still lambda 1, lambda 2. So lambda 1, lambda 2, d2f over dy dx, of course that wasn't really well written, plus another one, lambda 2 times lambda 1 times d2 df dx, so that makes it 2 times here, okay, and plus lambda 2 square d2f over dy square. Okay, very similarly, you're going to get that d2f over dy square. Maybe you can take some time later on to check that you are able to redo this, okay, to redo exactly this calculation. That's just going to be so, well, it's just like the lambdas are equal to 1, so d2f over dx squared plus 2d2f dy dx plus d2f over dy square, and finally I would have my d2f over dx dy given by, well, we want to make, let's take the first one, derivative according to y of the first one we had found, meaning this, sorry about that, this one here, okay, so lambda 1 df over dx plus lambda 2 df over dy, so lambda 1 df over dx plus lambda 2 df over dy. Don't hesitate to do it at the same time as I'm doing it. Okay, so that's just going to be lambda 1, so that's going to be df over dx over dy d2f over dx2 plus lambda 1 again times d2f over dy dx. Okay, that's for the first term, and then the second term becomes lambda 2 times d2f over dx dy plus lambda 2 again d2f over dy square. Okay, so that's now if you sum all the initial term that we wanted to substitute was this one, a1 d2f over dx2 plus a2 d2f over dx dy plus a3 times d2f over dy square. That is going to be equal to something. Well, if you use the three components that the three partial derivatives we computed, you're going to get something like d2f over dx capital X squared. So I'm just using the new derivatives, and I get some new coefficients that we will give explicitly a bit later. Okay, plus I3 d2f over dy squared. Okay, equals to whatever comes on the other side of your equation. Thing is that those A1, A2, and A3, they have some, if you give them explicitly, they will be given by A1 is actually small a1 lambda 1 square plus a2 lambda 1 plus a3. Okay, where is that coming from? Okay, let's have a look. It's the term that comes for the d2f over dx2. Okay, so that one comes from the cross derivative, right? So that one corresponds to the cross derivative. Cross derivative, I've got an a2, the d2f over dx square comes with a lambda 1, so a2 times lambda 1, right? That's this one. The other terms are going to come from, so when we're doing this, we had obtained this term for the df tilde over d capital X square, so I get it comes with the lambda 1 square, and the one for the d2f dy square is this one, so with just a coefficient of 1. That's why the one that comes with an A3 here comes with a coefficient of 1. This is why you only have A3, whereas for the one that came with the A1 coefficient comes with the A1 lambda 1 square. Okay, so that's for the first one. The second one, well, just trust me, this is what you will get. You can really easily check that at home. 2A1 lambda 1 lambda 2 plus A2 lambda 1 plus lambda 2 plus 2A3. Well, it's written in the document, and that would be a capital A3, and that one gives you A1 lambda 2 square plus A2 lambda 2 plus A3. Okay, then what do we have? So we have the, why did we do that? Because we can choose lambda 1 and lambda 2. Okay, and we can choose lambda 1 and lambda 2 in order to cancel out some of these terms, right? So we want to cancel out some of these A1, A2, or A3. Okay, so let us see. The lambda 1, if we want to cancel out, sorry, this term, or actually this term, what do we see? It's actually the same equation. It's something like A1 some lambda square plus A2 some lambda plus A3. Okay, so good news is that this is a second order differential equation, and you know that this is going to have some solutions. All right, so that may have some solutions, and that depends on the sign of the delta being so A2 square minus 4A1 A3. Okay, so assume that it's positive. You will have two roots. Okay, if this is positive, you can have two roots, lambda 1 and lambda 2. Choose those, and you're going to cancel out those outer terms. These and that are going to be 0 if you choose the right values, and then you will be left with a very much simpler differential equation that involves only this single second order term, right? Okay, so that's it. So let's see what are the other choices that we can make. All right, so it's I've been very far on the right hand side of this. Okay, so what do we have? We said it's all going to depend on the sign of this lambda term that rearranges the coefficients of the first equation, right? So if your delta is greater than 0, you're going to have what's called the hyperbolic case. If you have delta is equal to 0, you will have a parabolic case. And if you have delta smaller than 0, you have what's called the elliptic case. Okay, and then while those names were just chosen as in reference to the to some equations that we have for hyperbolas and parabolas and ellipses. Okay, so it doesn't really have a further meaning than that. Okay, so if your delta is greater than 0, well, let's go over this very quickly. You can choose lambda 1 and lambda 2 as the roots of the corresponding quadratic equation, and then you have, with your new variable, your equation has become this one. All right, your second order term has become that one. If ever you've got delta is equal to 0, then you have double roots. Well, we will choose lambda 1, for instance, well, lambda 2 to be equal to that double root, and lambda 1 to be different from 0, and you will see that from the formula of the double root, actually, that you can cancel A2 and A3. So again, you will get a simpler equation like this one, right, involving only one term. And if ever you don't have any other solutions, well, you can cancel out the A2 term, and you will have what is called well, we can choose lambda 1 and lambda 2 in order to cancel that a2 term. Let's see what it was. That a2 term is this one. And, well, you can find some corresponding values that can cancel these two terms, right? So you put this is equal to 0, and then you find lambda 1 as a function of lambda 2, and that's just going to, and then you have many choices, right? So you can cancel this term out, and you will have or left, well, you just got rid of one term, okay, the central cross derivative term. Okay, so that's it for quite a long introduction.